So the next chapter we want to look at is discussing the properties of solutions. So now that we've kind of built up on our thermodynamics topics a little bit more, we can revisit the formation of solutions and think about the energetics from the perspective of S, entropy, and G, the Gibbs free energy. So we'll start by talking about some of that. We'll look into some other units we can use for reporting concentration, and so I'll show you how to do some of those calculations, and then in the next section after this, we'll start to talk about some of the properties of solutions that we're interested in studying, like vapor pressure, boiling point elevation, all that sort of stuff. So just simply when we talk about a solution, we're referring to a homogeneous mixture of two or more pure substances, and it's always going to consist of one or more solutes and one solvent. So no matter what, when we think about this, the solvent is going to be whatever the major component is. So for most of our applications, it's going to be water, but it doesn't have to be. There could be other examples. And then solute, that could be just one thing or more than one thing, but these are whatever the minor components are. So there's some examples here of different solutions. We can talk about a gas solution, like air is primarily made up of nitrogen, but there are also other things in there like oxygen and carbon dioxide and methane. Most of our interest, like I said, is in thinking about liquid solutions where we've dissolved something into a liquid. So the solvent would be a liquid like water, and the solute would be whatever we dissolved in it. We'll be thinking about stuff like alcohol or salts when we think about this. So we can also think about what's going on in terms of intermolecular forces when we form a solution. So you may have talked a little bit about this at the end of the first semester class, but this starts to give us a good picture of exactly what's going on. So when we think about what happens in a solution, we're considering the intermolecular forces between solute and solvent. And these need to be enough to overcome the original pure solute reaction or interactions and pure solvent interactions. So what the picture is showing is our solid solute. We could imagine it's something like sodium chloride, and then it's surrounded by water molecules. So that's prior to the formation of solution, where all the solid is together and then all the liquid is on its own surrounding it, but we haven't mixed the two together yet. So when we think about what's happening in the formation of a solution, we can use this series of pictures to kind of think about exactly what's going on. So that far left picture is the same as what we started with, beginning with the solute isolated from the solvent. And then in the middle picture, you're starting to see where solute molecules or ions are getting surrounded by water molecules, and that's where we're starting to get the formation of a solution. And then finally at the right, you see really a fully developed solution where solute and solvent are intermingled, and there's no isolated solute and really no isolated solvent. So what we can use to describe what's going on here, we call them solvates. When we start to have our particles surrounded by solvent molecules, that's what we're looking for. And in the case where the solvent is water, then we can call those hydrates. So you could sort of see what was going on in the pictures there, but this kind of depicts it a little bit more clearly. So if we imagine taking sodium chloride and then mixing it with water, our understanding is that we'll get sodium cation dissolved in water and chloride anion dissolved in water. And that's what the picture here is really showing us. where on the top I've got these sodium ions that are surrounded by water molecules. Notice the oxygen side of water, the more electronegative side, is pointing towards the positively charged sodium. And then down on the bottom, you can see that the chloride ion is surrounded by water, but now it's the other way around, with the hydrogen side, the less electronegative side, really the electron deficient side, pointing towards the negatively charged ion. So that's what we're looking at here. You can kind of see that octahedral arrangement of water molecules around the ion, and that's pretty typical for what happens when we hydrate with water. So here it comes up with an important point in the words here. It just says, if an ionic salt is soluble in water, it is because the ion-dipole interactions, that's what we're depicting on the left here, are strong enough to overcome the lattice energy of the salt crystal. So when we talk about lattice energy, that's the energy associated with something like sodium chloride, where we talk about how tightly held the sodium and chloride ions are to each other. So the only way I'm going to talk an ionic solid into dissolving in water is if we can give enough energy to make up for the energy it has in its favorable interactions in the solid state, and that's what we refer to as the lattice energy. So we want to think about our picture of what's really going on in terms of solution formation from isolated solute and solvent to mixed together solute and solvent. And more importantly, we want to start to think about what it means energetically as we look at it. So we're breaking this down into 3 processes. And so first, we need the energy associated with separating the solute particles from each other. So something like lattice energy could come into play there. And that's going to cost us energy, right? To pull particles apart, it's always going to cost us energy. And then separately, I need to pull apart the solvent molecules from each other. So we're breaking these solute-solute interactions and solvent-solvent interactions, and we're replacing all of it with new interactions between solute and solvent. So now the last picture is saying, now that we've pulled the solute apart from other solute particles, pulled the solvent apart from other solvent particles, now we're going to mix those together. So that's going to be the only favorable part. So in a simple picture of what's going on, we'd say the only way a solution is going to form is if the energy of the new interaction counteracts the old energies of interaction. And that's partly true, but not 100% true. So if we think about a dissolving process, there are lots of solids that if I pour them into water, they'll dissolve, and in dissolving, energy will be released, and I could observe that energy being released as the solute dissolves into the solvent, and then we'd be able to say, well, the dissolving process is exothermic. But now here we're asking, now that we have a picture of what dissolving is, why do endothermic processes occur? And so now we're in a position to think about this, because now we know this equation, delta G equals delta H minus T delta S. And now we know if delta G is less than 0, we have a spontaneous process, meaning without any outside intervention, this process is going to occur. So that's where we're going to get as we think about this picture overall. So here it says, things do not tend to occur spontaneously unless the energy of the system is lowered. So now in this picture, we're saying, what if the energy after solution formation is higher than the isolated energy for solvent and solute? And I guess I should be more specific here. It's just talking about heat flow, just about the enthalpy part of this. So remember, when we talk about our equation, we've got enthalpy, and we've got entropy related to the disorder. And it turns out that entropy is a very important component of the formation of a solution, and that should make reasonable sense. So if I dissolve something like ammonium nitrate in water, if I measure the heat flow in a calorimeter for dissolving ammonium nitrate in water, I would observe that the temperature of the water in my calorimeter would decrease because heat is required to dissolve ammonium nitrate in water. So we'd actually observe that the water around it is cooling down. And we can sort of rely on this idea when we think about making a cold pack. Those things usually have some solid in them that when I dissolve it in water, it's an endothermic process, and it starts to cool down rapidly. So heat is required to dissolve ammonium nitrate in water. So essentially we're saying this process with water making ammonium aqueous and nitrate aqueous, we're going to say from our understanding that delta H is greater than 0. It's an endothermic process. So then a fair question would be, well, if it's endothermic, if it requires heat to take place, why does it take place at all? And again, that's why we come back to delta G equals delta H minus T delta S to think that whether something occurs or not is based on whether it's spontaneous or not, right? Spontaneous means that it occurs without any outside intervention. So if we really want to talk about something being energetically downhill, we can't just think about delta H, the enthalpy change. We need to think about it from the perspective of delta G, the Gibbs free energy change. And when we think about that, then the entropy change becomes an important part of our picture. So that's what we want to say here, that enthalpy is only part of the picture. And so again, with our equation, delta G equals delta H minus T delta S, for any solution formation, we're increasing the disorder, right? We used to have solid by itself and solvent by itself, and now we have them all intermingled. So as soon as we make a solution, the disorder increases because we've mixed together all these particles. So then when we come to our equation and look at delta S, when that is positive, it makes it possible for us to get a negative delta G even if delta H is positive. So our explanation for why an endothermic process could be spontaneous would be if the entropy change is enough to make up for it. And generally speaking, the entropy change will be substantial every time I make a solution. Okay, so this kind of says the same thing. Even though enthalpy may increase, the overall energy, so there it's talking about the Gibbs free energy of the system, can still decrease if the system becomes more disordered. So even if delta H is positive and delta S is positive, we'll still be able to get a case where delta G could be negative. And so that's where you can start to think about the temperature component of dissolving as well, that at a higher temperature, the entropy change could have a greater effect on whether something is negative or positive Gibbs free energy. So then we can think about the idea that at higher temperature, the entropy change portion becomes more important. So maybe a dissolving process that wasn't spontaneous at a low temperature will become spontaneous at a higher temperature. All right, so we just really wanted to think about that concept qualitatively because it's a fair question to ask. If a process is endothermic, why does it happen at all? And the answer is, even if it's endothermic, it can happen as long as the entropy change is substantial enough to counteract it. And we saw problems like that in the thermodynamics chapter. I just referred to it as a certain reaction or a certain chemical process. But when you were working with the equation, again, delta G equals delta H minus T delta S, we were asking at times to say, well, what temperature will it require to make this process spontaneous? So now we can think of an actual example of that, and that would be the formation of a solution. Okay, so really no math to do there, just kind of qualitatively understanding how an endothermic process is going to be able to be spontaneous. Okay, so more vocabulary here, talking about how we would describe a solution. Pretty straightforward stuff here. When we talk about a saturated solution, this kind of goes back to thinking about the KSP value, but a saturated solution means that the solvent is holding the maximum amount of solute that it's able to at a particular temperature. And really, that's what the KSP value is telling us, that it's reporting the maximum amount of solute that I can dissolve into my solvent. And K values do have some temperature dependence. We didn't talk a ton about that, but it is something that we need to consider. So when we really think about what is going on in a saturated solution, it still is an equilibrium. So even though our viewpoint is that nothing is changing, in reality, the rate of dissolving and the rate of crystallizing is identical, so it looks like nothing is happening. So that's saying dissolved solute is in dynamic equilibrium with solid solute particles. But our observation is a saturated solution with the maximum possible amount of solute dissolved in the solvent. Well, if saturated means that the solution is maxed out, then unsaturated would mean that we haven't added the maximum amount of solute. We can still add more in order to get to a saturated solution. The last term is a little bit trickier. Now we're talking about a supersaturated solution. So terminology-wise, this should make sense as well. Supersaturated means we are past the equilibrium constant amount. We're beyond what KSP tells us. We've got more solute than it normally would at this particular temperature. So generally speaking, the way that I get a supersaturated solution is at a higher temperature, I dissolve as much as I possibly can and then allow this solution to cool down. So there are times where as I cool back down, I'll get to a lower temperature where now the solvent is holding more solute than it normally would, and that would be a supersaturated solution. So it turns out when we get to these types of solutions, we would say that they're unstable and it'll be really easy to cause crystallization. It could be something as simple as just setting it down on the counter a little bit harder than normal, that would induce crystallization, or you scratch the walls of the container. That creates an imperfection in the glass that creates a good template for the first crystals to form, and then all of a sudden we have a whole lot of crystallization taking place. The last method to get a supersaturated solution to crystallize is to add what we call a seed crystal. So if we put a little bit of the solid that we're trying to get to crystallize out into our solution, then that will make the solid form. So crystallization is really a complicated thing. So we do a lot of work with supersaturated solutions where we're trying to cool something down gradually to get crystals to form, and that's where that comes into play. All right, so when we want to talk about solubility a little bit more, one of the most popular phrases that we use is to say like dissolves like. That's a very common thing that we say when we're talking about what's going on in solubility. And more than that, we would say polar substances, so things with a permanent dipole, tend to dissolve in polar solvents, and nonpolar substances tend to dissolve in nonpolar solvents. So in this particular table, polarity is increasing from top to bottom. These are all organic molecules that we're looking at, but what's happening is the hydrocarbon part of it, the nonpolar portion, is increasing as I increase the carbon chain length. And so in the first three, with small carbon chains, you can see that these are all things that will dissolve in water. Water is kind of the most polar solvent we really have. But then everything is dissolving in a nonpolar solvent. So polar, nonpolar. And so this general principle that like dissolves like, it's really well demonstrated here that the small alcohol molecules are dissolving fine in water, and then the smallest alcohol molecule will not dissolve in hexane, the nonpolar solvent, but everything else will. So the more similar they are in structure, the more likely it is that one will dissolve in the other, and that's what we mean when we say like dissolves like. All right, so all that was kind of qualitative, some vocabulary stuff, just conceptualizing what's going on in terms of the formation of a solution. But the main concepts that we want to look at in this chapter are what we call colligative properties. And these are properties that a solution possesses just based on however many particles there are in that solution. So one of the things that we're going to need in order to make that type of calculation logical is we're going to need a temperature independent unit of concentration. And more important than that, we need a temperature independent unit of concentration that we can easily translate into a number of particles. So ideally we need a molar amount incorporated into this. So briefly, I'm just going to tell you about a few different concentration units we could consider, and then we'll focus on one in particular, which is what we want, a temperature-independent concentration unit that includes moles. So we have all sorts of options, right? We can use mass percentage, where that's just a gram-based amount, the mass of solute divided by the total mass of solution. That's something that we can do. There's plenty of things that we buy as solutions that are reported to us as a mass percentage. When we get to much less concentrated amounts, and you saw this when you did the titration to figure out the amount of calcium carbonate, the water hardness, if the concentration is really low for something, then we could report it as ppm, parts per million, where we just take the mass of whatever we're interested in divided by the total mass, and then that's the parts per one. If we want to know the parts per million, then that's when we would multiply by 10 to the 6th. If we have an even lower value of substance, a lower concentration of substance, then we could get parts per billion. So same thing, we would calculate the parts per one mass unit and then multiply that by 10 to the 9th to report it as, rather than per one unit, per 1 billion units. One of the concentration units that we'll use in some of these calculations, you should have seen this in the gas law section of General Chemistry 1, but if you didn't, that's okay. Here we talk about the mole fraction, and so that's the moles of one substance divided by the total moles. So if I just had A and B, then the mole fraction for A would be the moles of A divided by the moles of A plus the moles of B. And you should have seen this, I think, as it relates to Dalton's law and some of the mole fraction stuff with regard to gas laws, and we'll see a little bit of that here. This bullet point mentions here that in some applications, this is referring to our application, you're going to get the mole fraction of the solvent, not the solute, so it just says make sure you're finding the one that you actually need. Molarity is old news. That's one we've talked plenty about before, and hopefully that's something you feel comfortable doing all sorts of calculations with, and we do that all the time, mostly in the lab, but hopefully that's all fine. But here's a very important point, and that is that volume is temperature dependent. So the numerator here has volume units, so in theory, molarity is going to vary a little bit with temperature. And so what we're going to be interested in when we start to study the properties of solutions is being able to have a quantity that we can use to describe the solution way down by its freezing point as well as way up by its boiling point. So for that reason, molarity isn't really going to work for that application, and that's why we're going to have to introduce a new concentration unit. And so, really not to confuse you, but this is the way the units are. We've got molarity, moles per liter, and molality, moles per kilogram. And so what's really important here is the numerator is solute and the denominator is solvent. So it's not solute over the total solution, it's solute divided by solvent. But the most important thing is the value in the denominator is in terms of kilograms. So now that I've got a mass unit to describe my solvent, that's going to be something that's temperature independent, and that's the goal. So we'd like to be able to easily go back and forth between molarity and molality, because for most applications, molarity is the best way for us to express concentration. It lets us easily do the kinds of calculations that we want to do. But in the rare case where we want to do some temperature independent calculations on a solution, that's when we would need to use molality. So, like I said, one of the most helpful things to be able to do is, knowing the molarity of the solution, be able to figure out the molality of the solution if we want to switch over to that. All right, so here's a flow chart that describes the process for doing this. And honestly, the flow chart makes it sound more complicated than it actually is. So the values that you'll need are the density and the solution volume. With that information, you should be able to figure out most of what you need to. So depending on which way you're going, we'd follow the flow chart one way or the other, but generally speaking, we want to go from molarity to molality. So once we have the volume and the density, that'll make it easy to get the total solution mass. In order to get the solvent and solute masses, that's what we'll get from the molarity, right? The molarity will tell me the moles of solute, which I can then change into the grams of solute, and then I know the mass of the solvent will just be whatever's left over. And that's how I'll get from moles or molarity to molality. So let me show you a worked out example, and then we'll do another one together just so you can kind of see how this would go. Okay, so like I said, our goal is to be able to fairly easily convert from molarity to molality. So you can see in this case, they're asking us to solve for the molality. So now here, what is the molality of a 5.86 molar ethanol, C2H5OH solution with a density of 0.927 grams per milliliter. So we understand this is what we want. In the numerator, we want moles of solute. So that's taken care of, right? Molarity, the numerator, is also moles of solute. So it'll always be true that whatever's in the numerator of molarity will also be in the numerator of molality. So the first thing that we want to do to take advantage of the information we have is assume that we have 1 liter of solution, because then we can directly translate the molarity into a number of moles. And so once we know the number of moles, we use the molar mass, and then we're able to calculate a gram amount for the solute. We also know the density of the solution, and again, with our assumption of 1 liter, that'll give us an easy way to figure out the mass of the solution. So since its density is 0.927 and we have 1,000 milliliters from our 1 liter assumption, that means the total solution weighs 927 grams. So now I know the total solution mass as well as the mass attributed just to the solute, to the ethanol that's dissolved in my water. And so now I'm able to figure out the grams of solvent, and then I want to have it in kilograms. That's the way molality works, that it's moles per kilogram. So now I've got that value, right? So moles of solute, it's just the same numerator as it was for molarity, and all I had to solve for was what goes in the denominator, and that's the mass of the solvent. So using the assumption of 1 liter, I know how many moles of solvent I have, and then I can use its molar mass, moles of solute. I can use the molar mass of the solute to figure out grams. Using the density, I know the total mass of the solution. Then I subtract solute from the solution to get the solvent, and then that's what I know to convert into kilograms and put into the denominator. So at the end of this, we say that for this particular set of conditions, 5.86 molar will be 8.92 molal. All right, so I think it makes more sense to look at that way rather than on the flow chart, but let's do one more just to make sure it's making okay sense. Let me jump out of here real quick. Okay, so let me give you some information. So let's say we have 885 milliliters of 2.25 molar, I'm going to say glucose, C6H12O6, and the density is 1.21 grams per milliliter, and then we want to know what is the molality. So we want to figure out the total solution mass. We want to figure out the mass just of solute. That'll give us the mass of solvent that we can then change into kilograms. So we'll say mass of solution. And that's going to be 885 milliliters times 1.21 grams per 1 milliliter. And rounding to 3 significant figures, that gives me 1070 grams. Okay, then we want to know the mass of the solute, and that's going to be 2.25 moles C6H12O6, and if I figure that out, it's 180.18 grams per 1 mole. That's the molar mass if I calculate it for C6H12O6. 3 significant figures there, I get 405 grams. So now I have the information I need to get the mass of the solvent. So that's just going to be 1070 minus 405, and that's 665 grams, which is 0.665 kilograms. So now I know how to calculate the molality. So now that's going to be moles of solute, which is just the same numerator as molarity, divided by kilograms of solvent. And so now I've got 2.25 moles. That didn't change, but now rather than 1 liter, it's 0.665 kilograms, and that's how I get my temperature independent concentration unit. And if I calculate that, I get 3.38 molal. Whoops, I drew an m, should be in lowercase m. And that's how we calculate that concentration. All right, so what we want to talk about next are some of the properties of these solutions. And these things are what we call colligative properties. So we want to talk about things like vapor pressure lowering, boiling point and melting point effects. And we'll talk a little bit, not too much, about osmotic pressure. So let me end this segment here, and then we'll pick up and do the rest of the slides in the